Hello everyone. Today we are going to present our topic on transportation and traffic routing using NetworkFlow. This project is part of our design and analysis of algorithm course. In this presentation, we will explain how graph theory helps in solving real-world traffic problems. Transportation systems today handle millions of vehicles and goods every day. In large cities, managing this movement becomes very complex. Traffic congestion is a major issue causing delays, pollution, and economic loss. So, we need efficient routing strategies to reduce these problems. This is where network flow algorithm come into play. A network flow is basically a graph model. In this model, nodes represent intersection or cities and edges represent roads. Each road has a capacity, which means how many vehicles it can handle. We also define a source, which is starting point, and a sink, which is destination. The goal is to send maximum number of vehicles from the source to the destination efficiently. In real life, we can map this concept easily. The source can be starting city or warehouse, and the sink can be destination city or market. Roads and highways are represented by edges, and their capacity shows the traffic limit. The flow represents the number of vehicles moving through the network. Coming to the problem statement. In urban areas, traffic congestion is a serious problem, especially during peak hours. Vehicles often crowd certain routes while other roads remain underused. This leads to a lot of time wastage and reduces productivity. So our goal is to maximize the travel time, maximize road usage and infrastructure efficiency, and avoid bottlenecks. To solve this problem, we use important algorithms. First is the Ford-Fulkerson algorithm, which finds the maximum flow using augmenting paths. Then we have the Edmond-Karp algorithm, which is an improvised version using BFS for better performance. We also have the Dijkstra algorithm for finding shortest paths, which is widely used in the GPS systems.
Now let's see how this works in practice. First, we model the road network as a graph. Then we assign capacities to each road. After that, we apply max flow algorithms to find optimal routes. Finally, the system dynamically adjusts routes based on traffic conditions. This diagram shows a simple network. Each edge has a capacity and flow is passed from source to destination. The red edge represents a bottleneck which limits the total flow. So even if other roads have high capacity, one bottleneck can restrict the overall traffic. Network flow has many real-world applications. It is used in smart traffic lights that adjust signals dynamically. GPS systems like Google Maps use it to find fastest routes. It also used in delivery optimization, emergency routing, and public transport planning. There are many advantages of using network flow. It reduces traffic congestion significantly. It saves fuel and travel time. It improves the usage of existing infrastructure. It also helps city planners to identify problem areas. However, there are some limitations. Real-time traffic changes are difficult to handle. The system depends on accurate data. Large networks require high computational power. Also, human behavior and unexpected events make prediction difficult. In real life, company in real life companies like Google use algorithms in Google Maps. Uber uses them to optimize driver routes and reduce travel time. Smart cities like Singapore use AI and network flow to manage traffic efficiently. To conclude, network flow provides a powerful way to model transportation systems. It helps reduce congestion, improve efficiency, and save time and fuel. It is already widely used and will play an even bigger role in future smart cities. Thank you for listening to our presentation. We are happy to answer any questions.